I'm Dayoung from Hanyang University. I'm glad to present our paper titled PRECYSE Predicting Cybersickness Using Transformer for Multimodal Time Series Sensor Data. Cybersickness is similar to motion sickness than user experience during VR interactions, characterized by symptoms such as nausea, dizziness, and disorientation. It's a significant barrier to user immersion in VR. Many research have used multimodal sensor data correlated to cybersickness and developed deep learning models for predicting cybersickness. However, there is still a lack of studies that apply recent algorithms to multimodal sensor data. The critical question is how to effectively integrate these latest algorithms with multimodal sensor data and how to store this data within the model for optimal performance. Based on this background, we propose a cybersickness prediction model that applies VR sensor data to a transformer, considering data format and multimodal data fusion method. And we have three research goals. The first one is to construct the multimodal sensor data for cybersickness in VR dataset. The second one is to provide comprehensive analysis with result for two embedding methods, considering sensor data processing and multimodal data fusion method. The last one is to analyze the relationship between cybersickness and sensor data with temporal characteristics by extracting feature importance. Before training model, we construct a MSS VR dataset through a user study. First, we selected VR videos. Although cybersickness can vary from person to person, it may or may not cause cybersickness depending on the content. So we prepare different content topics. We use the HTC Vive Pro Eye and the Empatica Pro wristband to collect multimodal sensor data. The study had 4 sessions, each involving 5 VR videos to measure participants' cybersickness level in real time. We used the fast motion sequence scale ranging from 0 to 20. Participants verbally reported their FMS score every 15 seconds during the videos. We collected sensor data from 45 participants involving eye movement, head movement, physiological signals, and FMS for labor. This slide shows our data processing pipeline for the MSS VR dataset. First, we perform downsampling 90 Hz to 25 Hz to remove duplicated values. Next, we apply normalize between 0 and 1 to ensure the model was trained in a more reliable way. For the MSS TTM model, normalized data was directly used. For MSS TTS, we applied the short-time Fourier transform to create a multimodal spectrograms, dividing the data into segments and transforming each one. We propose 2 methods for embedding sensor data format in transformer. The MSS TTN has separate spatial and temporal encoders that are trained to fit normalized sensor data, while MSS TTS uses a single transformer encoder designed to handle spectrograms that contain both spatial and temporal features. For MSS TTN, we first construct spatial transformer encoder ST. NT has a data features of a modality. The ST is applied to each data point NT. ST can learn a meaningful relationship between data features extracted from the same temporal index. The temporal transformer encoder TTE learns temporal characteristics based on a representation vector, which has characteristics of the relationship between temporal indexes. And then ST and TTE were applied to each modality. The extracted MLP heads were concatenated and cybersickness was predicted. For MSS TTS, as the spectrogram contains both spatial and temporal characteristics, the data processing is important. The transformer retains the vanilla structure and is applied to each modality. In this evaluation study, we evaluated different components of our method. MSS TTN achieved the best performance of performing the integrated ST and TT, and MSS TTS showed better performance than ST. This suggests that learning the characteristics of each modality through independent encoders and then fusing them was effective. On the other hand, MSSTTM performed worse than MSSTTM, reinforcing that normalized sensor data is more efficient than spectrograms. We compared the performance of previous cybersickness prediction models using both our dataset and a public physiological dataset. Our model MSSTTN showed the best performance across most metrics on both datasets. We analyzed feature importance over time to understand which features influence cybersickness prediction. Through multi-head self-attention in MSSTTN, we calculated the similarity of each input to the cybersickness level and averaged the result to obtain the total attention weight. Users left-right and front-back gaze shift, along with left-right head position X, play a key role in occurring cybersickness during VR content exploration. During the middle phase, users tend to explore the VR environment more actively, likely due to heightened immersion and curiosity after initial adaptation. EDA consistently showed a high correlation with cybersickness across all phases, confirming its reliability as a quantitative indicator. Normalized sensor data outperforms spectrograms likely due to frequency, resolution, and time window limitation in cybersickness context. It may be related to the outdated transform model, suggesting improvements with newer models like LLMs. Our contributions are to enhance data preparation and applicability using newer models in future. Key data features over time, particularly eye movement, strongly correlated with cybersickness. Given the passive VR environments, further research is needed to validate the model in other environments and ensure real-world applicability. Thank you for listening.